Right, so good morning, and depending on where you are, good evening or so, you're very early morning in US. I am Ashot Gasparian here, and I'm representing PRad project in Jefferson laboratory. And this is experiment result which doesn't give my friend Jan to sleep nighttime. Okay? Though looking on this fresh and fresher view, I could believe that, so we sleep very well, actually. And I will talk about this experiment, and I will focus on what's the difference between us and Jan, who is representing magnetic spectrometry method. And also I will come to second experiment, which actually we also trying to see what's the difference. That's PRad 2, mostly designed for that purpose, and I will update you where we are with that project. With that said, I will just go this slide very briefly, because some of students are here. Again, this is electron scattering technique. Bottom this one, upper one is the atomic spectroscopy method, and in an electron scattering method, we for sure we have electron proton and muon proton scattering, like news is coming soon, and we hope to see that as soon as possible. And the same way, when we measure outcome of events versus energy and angle of a scattered electron, we try to extract cross sections here. And those cross sections for sure depend from 2 form factors, electric and magnetic form factor there, right? And the whole thing here in first difference between us and the standard magnetic spectrometer method is this second term, magnetic term, is very small. Basically, we ignore other than the last 2-3 points. Okay? And for just magnitude, for our last point, this term is a GM term, is a 0.6% only, and we take from your field and add that term artificial. It's very small term. So basically, we deal only with this one, and this angle, small angles. Angles are 1, 2, 3 degrees, right? Scattering angle. I'm coming to say that, show that soon. And with that, things are very easy. Once you have cross section, you can extract for factor. Once you have for factor, then you can fit that, and slope is your radius, which we are talking about last 10 years, much intensively. But a few remarks here, other than what the previous speakers they did, and Jan emphasized very much. I want to just point out our definition of radius. Right? Definition of our charge radius is a slope of 4 factor at q square 0 point. That's definition. Q square 0 point. It's not any other q square. And after other than from that, we can have two outcomes. That this is not measurable quantity, right? This is only fitable quantity. We cannot measure it experimentally. We have to be careful when we know that. So therefore, we have to go as closer to q square, though Jan showed that it's difficult. Sure, it's difficult. We agree that. But we have to, everything is difficult. Right? All easy things are done 100 years ago. Right? We have to try to find the ways to go to more accurate result and more accurate result. So 2 things. We have to make a precision experiment and go as close as possible q square. And also, since that's third outcome also, since that's a result of feed, we have to get a wider range of q square to have a good level and stable feed. These 3 things is basics of this business. And let me show how we are solving this problem. Well, before going there, for audience, young audience, I'll show you that this thing was measured 60 or 70 years ago, right? Electron proton scattering, and that was Stanford University, a small lab, right? Done by the Hofstadter, famous Hofstadter. And by eye, he just fit that curve as I'm talking about, and he got 0.7. Let me see here, 0.7 for Fermi. And for that, part of that he get Nobel Prize, not only for this, but that was part of that. And take here from information is that the first one was a 0.7, 0.8 fairly, not larger than that, right? So as we conclude from that 0.7, we get in 2010 about 0.88, Jan's last measurement. And this is big, actually changed during 60 years, right? That created for sure part of our proton puzzle, which was talked about that, and that was a result of this 2 muonic experiment. Difference was 4.5%, but it was about 8 sigma, and that was big problem because of not only proton radius, but the Rydberg constant, which was mentioned before, that also is probably more important for physics than this proton radius problem. So here we've been in 10 years ago about, and we decided that since there is no much help from theory simulations to find out this difference, then we have to try parallel to have a high accuracy measurement. And that was actually coming from electron-proton scattering, new type experiment, not repeating electromagnetic spectrometer method. And also next one was muonic scattering, which news came about same years, and hope they will deliver results. So few things which I want to, because that's a major goal for my talk here, is to compare difference between PRad and spectrometer method, right? I agree that when we go to use calorimeter technique, we are losing resolution in energy and position also, right? So that we are losing. But what we are gaining is that important thing that we gain is at the same time, same experimental setting, we are measuring cross-section of this process in wider Q-square range without changing any parameter. And I want to comment to Jan's comment. He's right that we are using two energies. It's not written here. Next one, 1 and 2 GeV. That's mostly for not for using the feed. We separately feed them and result is same, but for checking our consistency of data. And they are exactly sitting on tails each other. That's the major design purpose of that, and I'm sure I will emphasize that later. So that's calorimeter method. So we are getting in one set we are getting a larger Q-square range, and that measurement also coming with a smaller angles, and that's connecting to this today's workshop. At smaller angles, 1 degree or 0.6 degree, we are going to up to that down, and a few degree entire data is up to 4 degree data. So at these angles, I think in our case, effect of radiative corrections are not problem, because they are about 1-2% all in that interval. How much error we can do, and instead of that, I will emphasize that a magnetic spectrometer method has that problem possibly. Okay, I will come to that. Now, what problem we may have, and I will also show later that distribution, we may have a little problem with extraction of non-elastic, not elastic contribution at going higher and higher Q-square range. And that's actually a major reason we are designing upgraded experiment PRad 2 to address that problem. And I will show how we're going to do. Now, one more thing I emphasize difference is that in case of magnetic spectrometer method, you are limited with Q-square minimum range. That's for sure. Angle is there, right? Typical resolutions are energy in angle is good, but you have a problem of controlling cross section for each data byte, right? Because you have to change angle from one angle to another angle, and that will introduce possible not control of acceptances and other things, and that's a standard problem in magnetic spectrometer method. And most importantly, when we try to use that technique for proton radius fitting, right? So that's I will emphasize that I see bigger difference there, right, between that. And because of that, Jan is using in this, I take from his publication, I guess 1,300 data set to feed this thing. And they claim that they have a good fit, spline fit, but still each data interval has a different normalization. This we don't have. What we have is one line. We don't normalize data bytes because it's one measurement. I will come to that. And I will emphasize that this, I see that's bigger difference, one bigger difference, other than systematic errors. So with that said.
Can I interrupt that?
Yes.
Oh, give me the microphone.
Yeah. Wait.
I think that's a trade-off, right? What we have to do is we have to normalize these groups by using one of the spectrometers as a normalization source. And you have to use the Muller to normalize the acceptance and the efficiency of your detector, because every data point is measured with a different part of the detector. So it's, I think, I mean, it's complementary, but I wouldn't say that any of these is better than the other.
Actually, I will go further. I will say no. I disagree because yes, with second spectrometer, you are dealing with an luminosity control.
Yeah.
But the changing acceptance is big issue.
Well, the acceptance doesn't change. The detector is the same. Well, I would argue if you move the spectrometer around, the acceptance is better controlled than if you go to a different segment of your detector.
Well, let me argue
because that's different geometry, right?
No, different it's calorimeter. It's well-known stuff and uniform stuff and different angles.
Yeah, but every block has a different position.
No.
So
yeah, but it's very well known. It's controlled by 100 micrometers.
Yeah, and the acceptance of the spectrometer is on the same level.
Well, that's probably can argue offline also, but for sure, for extended target, different angle, let's say 20 degrees, 60 degrees, acceptance is problem. That's known thing in spectrometry. It's about 2-3%.
Ashot, I will formally complain, though I don't think it's a practical matter, that yeah, Jan has to make sure his detector response is uniform in time. You have to make sure your detector response is uniform in position. And so all the crystals have to have the same gain and the same effective thresholds in your gem chambers as well. So you do have a problem that you have to make sure is in good control. So you know, there's no free lunch.
No, that's
I mean, I don't think it's a practical problem as long as you have plenty of statistics and you know, good data to look at. But it is, you do have to deal with it. It doesn't come for free.
I completely agree that we all have to take about uniformity and knowledge of the detector. But today we are here, we're trying to understand where could be possible difference, right? I agree. I not only agree, that's a reality. We have a difference between PRad and magnetic spectrometer. We'll have to see where it's coming from, right? And I will continue to say that those are things which we have to see how to improve and how to compare better way. For sure, we don't have a problem of acceptance. It's a calorimeter and size is no thing. But if you change angle in magnetic spectrum, possibly you do that. Okay. Well, as I said, but they try to have a different high levels fitting procedure, and they control that. And question is how well we control, right? So with that said, I will say in our case, in this case, I will say that Proton PRad experiment most likely has a question of how we control inelastic contributions, because our energy resolution is small, right? And magnetic spectrometer is about a factor of 100. For sure, there is no that question. But from other hand, most likely we don't have a radiative correction problem in our experiment.
Sorry,
but those do you
on that too, because that is actually sorry on that.
So you have a small radiative corrections mainly because your acceptance in the tail is so large. So it's a cancellation of of two terms in the radiative corrections, which makes your absolute radiative correction small. But it's actually a large correction minus a different large correction. And it's not clear that that means that the error is small. That is a very common misunderstanding of the small radiative corrections.
Let me try to understand. If you have
So you have a
distribution which is small, error on that one is small also.
no, because it's actually two radiative corrections. You once measure, so one you have a correction because elastic scattering is more complicated. And then you have another correction because you do not only measure elastic, you also measure inelastic, right? So inelastic in the sense of photon, right? Photon production, so produced extra photons.
Right.
And both of these terms can be,
Not only.
yeah,
Not only.
also the other stuff, but that's right, the radiative part of the tail. And so if you go down in the tail, you get more and more radiative tail, which makes the total size of the correction small. You can actually find a point where it's 0, but that doesn't mean that the radiative correction has infinite precision, right? It's still a large term minus a different large term, which has different error sources. And I would say it's probably the absolute uncertainty goes up if you cut deep in the tail.
Well, okay, let me make my case and then we'll
Mhm.
come back. Okay. There are some points I agree, some points I disagree. Okay? If my effect is smaller, then I have to worry about less, right? That's the case. With this purpose, okay, we came calorimetric method in our so-called PRad measurement. And most important second part, I want to go faster here, is that using new type of window. This was at least arguably one of problem before all magnetic measurement before, right? So we changed this one, and I will show some result. This actually made a big difference. Gas flow, windowless gas flow target in this experiment. So two things: magnetic spectrum, changing the calorimeter method, and using new type of windowless target, which basically took off beam background. Basically, most cases. For sure, there are some problem also. We can argue later. Now, third thing which comes from this new method is that we are able to normalize entire thing to QED, well-known QED process, that Mueller scattering, which we measure parallel, not separate way, and we can have that with absolute precision. And my radiative corrections for Mueller one is the smallest, much smaller, because there is no additional 4 factors there. I guess experts will agree with this, and we did that. So with that said, we had the 2 runs, 1 GV and 2 GV. So this is different tip range, but mostly because we wanted to see how our data are talking to each other, and happily we get that one. Experiment started, proposal started 2012. We start putting all together in the 2016 winter, and by summer we already had the data, and it took 3 years before we published in Nature Journal in 2019. It was in Jefferson Laboratory. That's just aerial view of Jefferson Laboratory here. An experiment was done in hole B, the smallest hole, the hole B. I may have some picture close part of that one. Okay, let me emphasize what was experimental setup. Extremely simple. Probably this is one of latest experiment which is extremely simple. And I want to emphasize that once you go to precision measurement, you have to try maximal make extremely simple thing. Okay. Well, again, this is arguable thing, but I follow that philosophy. Beam comes from left to right, electron beam, that's 1 GV, 2 GV. There are some tagging system which was used only for calibration purposes. And the major thing here is a hydrogen gas flow target here without windows, right? And the scattering chamber about 5 meters long. And here is a big calorimeter, about 1 meter by 1 meter calorimeter. I will show you the picture in order to emphasize few things which is making problem. And there is GEM coordinate detector, which is making about 100 micrometer or less precision measurement of position. So we have energy and of calorimeter and pointing gem, which gives you a nice tracking. Not tracking, I'm saying, but in this experiment, we didn't have tracking capability. So we'll define angle by point and target position. Just a few simple words about simplified way of gas flow hydrogen target, windowless. Cryogenic gas is dropped from top and goes from this 2 millimeter windows where beam comes in, and we are pumping out with 4 or 5 high capacity pumps out of beam line. And that's a part of, you see, whole B looking from top to down, and this whole thing is our complicated all this stuff here. As you see, not that always easy when we see that one. And then we go my scattering chamber here, long one. And for scale, this is one of our postdoc that time here, and that scale gives you a little bit more scale of experiment. Most important difficulty what we had here is about 2 meter diameter window for vacuum box. This was a big issue, by the way, technically, not physically, right? And most importantly, as you see, beam line is attached to that window, 2 millimeter window here, and beam goes down through calorimeter. GEM is here, standard GEM technique, and this was the largest GEM at that time. I don't know if it's larger now. Position resolution is 72 micrometer, which allowed us to define Q square and angles all, and have good resolution in that parameter. Calorimeter. This was our Primex calorimeter, which is a crystal calorimeter inside, lead tungsten, and outside is lead glass. Now, this is the point which I want to make. Our high Q square data coming from this low resolution lead glass detectors. Okay? And the high and low Q square data coming from crystal part by angle, simple angle is, because energy is one. Okay, so that one we want to change now, PRad to experiment. This is model one of them. And as you see, beam is supposed to go through this about 4 by 4 centimeter hole through calorimeter. It's also technically challenging thing, but we did into experiment very successfully. Data, if we put data 1 GV, 2 GV, as you see about a good amount statistics, but still we need more. If you plot that energy versus angle, you will see elastically scattering protons, electrons from proton, and Mueller part, 1 electron from Mueller, right? And this part is lead glass part, this one is a crystal part as a resolution. This one is 1 wing of Q square ring of Mueller. Mueller was controlled highly over defined kinematics. We didn't have any problem with Mueller, as theoretically as also under radiative correction was done better for Mueller thing, and cross section is known very high precision. For proton electron proton scattering, as I said, there is a simple kinematics, and that's not a problem at all. Few words about, again, possible problems here. Is a background. We have to address this background, beam background. We had our design of this target at about 4 different positions. We could have a working condition, this one A, when this 20 Kelvin hydrogen is dropped here, but still there is some residual gas here and outside also. For that purpose, we had a second valve here, and we could repeat background condition in target. We measure this one also separately. And we could also pump out whole gas inside. And eventually we could retract the cell, hydrogen cell upwards. So those measurements we did. And as you see, if we subtract all this one, it's about 1% background here at 2 GV. Well, 1 GV is a little high. Okay? So subtracting 1% thing is easier than subtracting about 15–20%, which is coming from standard hydrogen, extended hydrogen target.
Sorry,
Now,
what's the
second-
problem on this? This is not true. Your percentages are very similar to what we had in mind.
We had about 12% at forward angles and less than 2% for most of the measurements, not 20%. So it's very, very compatible. It's just because the density of the target is so much better, higher.
Well, okay.
It's
Okay. All right.
doesn't make the experiment worse, but
This makes it worse.
it doesn't make your experiment
Ah.
worse, but I mean, we should stay fair.
All right, okay. So let me go follow this one and then, I have to go. Okay, here's a second part, which actually, I agree that we have weakness, right? Sure, if you go from high resolution magnetic spectrometer to colorimeter, you have to pay for that. And that pay comes here, as you see, this one is a low Q square cut, here, this line here. And this one is our inelastic background. So we believe that with this, we cut inelastic background condition contribution very well. But when we go to lead glass part where resolution is 3 times less versus crystal part, as you see, this demonstration is just one of Q square range. This is our cut level, and we still have about 1-2% contribution when we fit down our P. So that could be questioned, though we use best model here to fit our background data, as you see, right? And this one fit is, and this one is inelastic contribution on top of that. We changed this cut level many ways, right? As the question was there, and that's we're coming actually publishing a longer paper, and we will describe that whole thing there. And we contributed this error as in error bar is smaller, but in precision measurement, rely on any model. Myself, I will not repeat that experiment. If you rely on model, then it's accurate as model itself is accurate. And this inelastic shape is model, right? There is no measurement in this inelastic part. And we use Christie's model, that's here, all those fitting process, right? I want myself to have second experiment independent of any model. And that has to be done that way in order to trust the result. And that's actually what we're trying to change. We want to extend this condition to here, this Q square range also, where we have differences much, right? See, right? We agree at that part, we agree with you, right? That's what I will talk about a few minutes later. And this is standard thing, but I want to emphasize that we also, first time we used for this measurement, a ratio method. But we make a ratio with Mueller process, which is known much better, much controllable thing. And I will argue my colleague in Japan that carbon is not good target for ratio, to have ratio that way. Okay? So I will not stop here unless you have question. It's a standard technique, iteration technique, and normalization gives away all possible luminosity and possible actually acceptance problem also, depending on model or method we do. We did two ways. Yeah. Well, once you have that, you are extracting cross sections. It's 1 GV, 2 GV. There is supposed to be plot which compares two together. Yeah, maybe this one is 4 factor. The red one is a 1 GV and blue one is 2 GV. As you see, there's an overlap nice way. We've been happy with that. We never use Q square equals 0, Q square 0 equal 1 point. That's another difference between us and you guys, right? This point coming as a fit. And if you know that's this n parameter, which is difference is 0.1% only if you look at, it's not written on this plot. So n parameter is taking care about that normalization, right? I'm sorry?
How would you reproduce one? How well do you reproduce it?
That's what I'm talking about, less than 0.1%. Okay.
But it's still floating in the fit. So it's the same.
Kind of, yes, yes. But we are not explicitly using that one.
And is the Mueller normalization bin by bin, or is it one Mueller cross section?
It depends on range. Yeah. We apply two methods, yes, bin by bin and integral models. Okay. I feel your question, yes. Okay, so here's a picture before we trying to publish our paper. By the way, this one was 2 months before our publication. It's a York University result, good experiment. I will not go through because many times we discussed this here. And here is our point when we published 2 months after that, 2019. That's our point here, right? Sporting smaller radius for sure, that's coming problem. Unfortunately, yeah, I have one plot which is not as good as Jan has that one. And with this stage, I would say, we trying to come up with second measurement. Okay? Second measurement, basically addressing that difference, how well we are subtracting our high Q-square range in elastic part. That's our focus is that, and as I said, for that we want to use all calorimeter uniform. For this type of measurement, you have to make your detectors uniform. I agree with that. Okay? We have two types. And we are trying to get all lead tungsten crystal here, which is challenging job. Up to now, we haven't solved it. If I go to that point, we are still working on this problem. Second thing is that we want to attract, to make further this subtraction of backgrounds here with Jan mentioned that 2% still we want to control better. And that will be second gem on 40 centimeter distance here. Here is a helium environment is not much. We are adding too much background there. Helium bug basically between two gems. And that will allow us to select tracks which are coming from target basically. We didn't have in primary stuff. The rest is about same, only in this case we have one more addition here. We want to go to try to reach to 10 to minus 5 Q-square again. Our first experiment was 10 to minus 4. I didn't have time to mention that in this new experiment, we are planning to get 10 to minus 5, and that's a another bigger point for this type of data. I will agree that is challenging, very challenging, I agree, but we have that capability to do. And the way we will try to do is we will veto small angle Mueller, which are technically problem, by adding scintillator detectors here, tiny small scintillator detectors, vetoing first one pair of Mueller. And that's extensive Monte Carlo showed that is possible. Absolute cross section, we have to come to see. Okay? But again, since we are normalizing to Mueller, I think that's will give us a good chance to reach that useful data in 10 to minus 5 Q-square range. This is picture which Jan had better one, but again, I guess it's same, right? Yeah.
Yeah, it's just not logarithmic Q-square.
Yes, yes, you have logarithmic one, right? Okay. I will try to borrow it from you sometime. Okay, so here's a difference which we are focusing. Okay, it could be again, to me, either before all magnetic spectrometer data, including the experiment, may have some problem of normalization of those things, or subtraction of radiative tails, radiative correction, because you guys are using about 50, 60, 70 degrees sometimes, right? If I'm correct. This part?
The discrepant data points are the left.
Yeah, this Q-square is lead glass, yes.
Yeah, but the lead glass is also in the lower energy, and they have the agreement is great. So I don't think lead glass.
That's true.
Something by the lead glass at a higher energy.
That's also true, because we have data which is overlapping areas, lead glass and tungsten. That agreement is there, but the agreement on which level is a question.
Certainly better than the 3% you see.
Well,
I don't think the lead glass can explain.
I will tend to agree with you. That's why we publish our PRad data, because we understood that that's a reliable method. But every question has to be addressed.
And I've always
Uniformity is issue and other things is issue.
I've always tried to express my concern that there might be backgrounds in the lead glass region that could come from gas that goes upstream the beam pipe, and it's detected at higher crystal transverse number, but it's actually small angle scattering, but detected at seemingly larger reconstructed angle. And I'm not sure if your background subtraction scheme that you demonstrated captures all of that. So my suspicion or worry was always that you have an additional source of background that is unaccounted for.
I agree with that point, yes. Again, in experiment, there are many things which we cannot control much, but for that purpose, we are adding tracking. That's what we are. So uniform calorimeter and tracking to get point of target defined. And that will take care about the possible background. I cannot refuse that there is no. Will be few percent there, yes.
Vertexing backwards.
Yes.
Okay.
Yes. In PRad 1, we didn't have tracking. We had only one coordinate. Right? And that was close to calorimeter. It doesn't allow you to reconstruct back. Right? Now we will have 3 points. Gen 1, Gen 2, 40 centimeter, and calorimeter is about 30 centimeter back. So the 3 points will define that. I don't have with me resolution and target area, but that's good enough to take care about that background. So you are probably waiting for my final slide, where we are. We want to have a 4 times better precision than PRad 1. And this is just arbitrary, as you can understand, but it's in the same point. On this point, can go here, come here. Well, if Jan is happy, lucky, it can go to here, right? And then agree with his result, and we're out of business. We don't want it. Right? We want to avoid it. Right? Thank you very much.
All right, thank you very much, Ashot. We have questions. I'm going to go to Jan first.
Yeah, thank you. I actually have 2 questions. So for PRad 2, are you planning a blinded analysis?
Yes.
That's good. That's good.
Yeah.
And for PRad, I mean, we do the same for Muse. I know it's a real headache for scattering experiment to do this, but I think we need to do this.
Yeah.
And for PRad 1, how did you determine the gem efficiencies?
Okay. We had a, let me go about that. Schematically. Well, we calibrate this calorimeter, and gems are attached to this frame.
Mm-hmm.
And by photon beam with known energy tagger, right? This is the system, we use that one. And in that case, for calorimeter moved every position about photon.
Electron beam, you mean?
Yes.
Okay.
And that calorimeter calibration and efficiency measurement. But for gems, we also had on photon, we had converters in order to calculate efficiency. So photon scintillator before gem and calorimeter. Together we define that one, and that take care about gem efficiency. But one more technique we use as a checking the point is a gem. If you see gem structure, let me show you how I pass. Our gem are, because of large size, consists of 2 parts. They have a left side, left part, and so they are overlapping range here, about 4 centimeters. So that whole strip, we measured absolute gem efficiency. It is the best technique because we have 2 together, right? The rest we don't have 2. That was about 96% plus.
Yeah, right, because I mean, what I've seen is that the gem efficiency changes quite a lot from the middle to the side, and I was a little puzzled by this, right? Because this, I mean, clearly, when if you underestimate your efficiency, you move your points up, right? That why, I mean, it just looked like a possible candidate for something which moves the points up.
If we use knowledge beam by beam, that takes about, does it change?
Yes, that's true. That's true.
But still, it's 2 particles that are detected versus
Second order.
Yeah.
Second order.
So if the single particle detection efficiency of the gem is high, then detecting two particles can be sufficiently accurately determined. But if the efficiency is not close to 100%, then the two particle efficiency will differ from the one particle efficiency by some margin, and then how well you can control it is another question. But I had another one.
96% around, yes.
Yeah, yeah. I had another concern. So the calorimeter detects photons, but it would not capture any initial state radiated photons, or does it?
Yeah, it's a good question. Let me make my own comment. In 1 or 2 months, we will publish a very good data we have, but because of this part we're busy. We are measuring radiative corrections. That's probably maybe first.
Yeah.
Because we have that capability. Our calorimeter measures both electron and photons. And data was analyzed already by Chao, one of our collaborators, and we probably will publish in 2 months. That was our agreement was.
Mm-hmm.
And there is good data. Yes.
Yeah, we saw in studies for Muse that if you do not have the knowledge of the initial state radiation at all, then the detection threshold becomes a sensitive parameter for the scattered lepton. And your lead glass calorimeter has some elasticity cut applied, as I saw, but the resolution was not.
No, that's only on data. We can play that on data.
Yeah.
In data taking period, calorimeter had about 20.
But there's an uncertainty enhancement effect due to not knowing about the initial state radiation, and that creates a radiative correction uncertainty.
That is in principle true, but I think at the cut point, this is dramatically less.
So the fact that they have an elasticity cut available.
It's not really deep in the tail.
Yeah,
right?
yeah.
I mean, at the end of the tail.
Yeah.
It's not.
So that's not a
close to the
concern
left
here.
side, but
Okay.
It's sufficiently close that the initial state rise doesn't boost it enough that it's a big effect.
Yeah, I agree. And also I want to add to that, look, we are measuring that radiation on magnetic spectrometer does. We have that in data. We can use in different ways. Right? It's additional control to experiment.
And the initial state radiation probably escapes because that goes down with the time.
That will be only for beam. The scattered electrons will carry it.
Yeah, so the one from but the initial state, that's the problematic one because that gives you a boost in the cross section because your effective Q squared.
Well, it's partially will be because it's 5 meters long and and this is 4 centimeters long. So
Yeah,
it's
so
small
almost
angle.
that, but small angle.
6.6 degrees.
You're done talking now, aren't you? Getting my steps in today. All right. Ron has a question, I think.
Sure. I think there are 3 points we've discussed before that haven't come up today, so I'll pile on. So the first thing is, if I remember correctly, the gem efficiencies were only determined to about 1% for the large angle, large Q squared points.
1%.
1% statistical uncertainty was shown for your gem efficiencies at the large angles. In Shang's thesis. I think that's from Shang's thesis, but maybe I misremember. Okay, so that was 1 point, although probably doesn't make a difference. A second point, which I think we've discussed in the past, is your lead glass calorimeter crystals were only calibrated in their efficiency down to something like 300 or 400 MeV in what you showed, but the molar electrons are all lower in momentum than that. And I think you explained this to me and it wasn't a problem, and I don't remember the explanation.
Explanation is that, yeah, that tagging system which we use simply has only 0.2 times beam energy. Right? You cannot
Right.
But
The basic comment was I wasn't sure of how good the molar normalization was for the low energy large angle molars because the calibration wasn't shown down to the energy of those molars.
Yes.
Right.
Let me finish that answer.
Sorry, Shah.
If it's a linear device, on linearity we're checking bigger interval of energy, 300 to 1 GeV, right? Linearity on, And it's known in your device. We can always extrapolate
But
there.
but 0 isn't the intercept.
Uh,
The intercept's not at 0.
Yes, but how much
Yeah.
that it will give you in the
Oh, it's a
final
few
physics
MeV.
result? Tiny, tiny, small thing.
Yeah, I don't know the sensitivity. All I know is the offset's a few MeV.
Yeah, but I will say it's
Mhm.
tiny, small.
And the third comment is relating to PRad 2 that these veto scintillators you have for the molar at small angles, you need to know their efficiency really well. It's it's easy to know a scintillator efficiency is 99 plus or minus 1%, but you need to get it better than that. And I don't know how much better. So you need to think about how well you have to know their efficiency and how you do that.
Do we need that efficiency to calculate
Uh,
your cross-section? Yeah.
I'm guessing you need to know the cross section to better than 1%, and I'm guessing if you don't do anything, you only know the efficiency to 1%. So you only know how much you suppress to 100% of what's left over.
Yes, I cannot
So-
bring you number, but that's Monte Carlo data only.
Yeah. So think
I
about
get
it.
the question, it's a good question. And we will calibrate that outside. Oh, okay, okay. Its memory comes, it's over 3 years ago. We have some special technique to calibrate efficiency, to measure efficiency of those things with large angle models.
Okay. Make sure you know it well. That's my basic comment.
Good, I agree.
Okay, I'm gonna go to Michael because he's closer, and then Sasha.
Just a quick one. Have you analyzed the radius with the two colorimeters separately, with the
Yes.
high color and with the LED glass for covering different regions?
Yes.
And how does
Yes.
that compare? How do
For
they
sure.
compare?
For sure we did, and that's why I'm saying we publish longer paper in which we will include that one, and I had that question also. We have even the distribution of radius with many different ways, and they are around 0.83 with some sigma is about 0.015 or something like that. I forget that distribution, but they agree with each other. After doing all those exercises, we decided that our data, whatever it is, supports smaller radius. It's not only 1 feet. We did 2 energies also separate.
I have a question to clarify terminology. Does it make sense to consider just initial state radiation when we have diagram with one radiated photon by itself is gauge non-invariant? So that's why like you have always add all contributions and only this makes sense, physical sense. So by itself with gauge non-invariant, I can like choose other gauge, have completely different numbers. So that's why if you just terminologically, it's probably not
First thing which I
good
want
thing to do.
say, we are not that at all dependent on initial state radiation. So whatever you
Yeah,
define-
I think it was more not to you exactly and to your experiment, but to general to community. Yeah, to general to community and to people.
Expert, they have something.
Yeah, who do.
With their experiments, we do like virtual quantum scattering where you detect an electron and a photon.
So I guess when people talk about initial state radiation, they make an approximation and they just take the logarithmic enhanced terms, which is gauge invariant. But you're of course right. Just doing this diagram alone is totally meaningless, right? In that sense.
Here is a result minus initial state radiation, as you see that big error bar. And Jan may comment on something. It's a difficult experiment, I would say.
So another comment on initial state radiation. From the theoretical perspective, of course, you have to include all the diagrams. Then you have your theory and you look at how your theoretical calculations or the theoretical correction affect kinematics of the experiment, right? So what is discussed here is kinematics of the experiment, how momenta are redistributed about how momenta are redistributed because of the radiation. So I wouldn't penalize experimentalists for saying initial state radiation as a conclusion.
All right, are there any other questions for Ashot? Okay. All right, let's thank our speaker.